working? Oh, okay. Yeah, hi, my name is Andrea. This is joint work with Francesca Falzon and Kenneth Paterson from ETH and Tianxin Tang from the University of Glasgow. Without telling too much about the title, I'll just start with a little example to motivate our work and show you what the setting is. Great, thanks. Okay, so little example, consider two banks. They maintain two lists of blocked IP addresses, and they decide to join forces and share these lists and sort of aggregate them in a combined block list, which they both use. Now there is the additional requirement that two banks learn nothing but the result in this process. In particular, they shouldn't learn the intersection of their inputs due to some policy or whatever. Now this is a classical example for the use case of an MPC protocol. However, while a secure MPC protocol doesn't leak anything about its input except for the intended output, the standard security notions don't consider what the output itself leaks about the inputs, in this case the union, especially not over multiple protocol invocations. So the scenario we consider is what happens if A gets a little curious and over multiple protocol invocations chooses its inputs maliciously to learn about B's input. A very simple example is that it could omit one input, one address in its input, and if it still observes the input, the address in the output, it has inferred a part of the intersection of their inputs, which it wasn't supposed to, right? This is a little bit artificial, but the deployment risks that we highlight with this are real because use cases often require repeated invocations over short periods of time with changing inputs, right? A little more real-world example of this is Apple's CSAM detection system, which you maybe know. This was proven secure in a cryptographic setting, but the functionality itself could be abused for surveillance purposes. And indeed, Apple had to shut down the project shortly after concerns about this were raised. Now, in academia, there is like a relatively fresh but growing line of work which considers MPC functionalities under this attack model. These works are mainly concerned with functionalities that compute some function over the intersection of two input sets. And in this work, we consider a different range of functionalities. In particular, union and union-related functionalities. We start off by describing an intersection recovery attack against the private set union functionality, as well as the private set union cardinality functionality. We then show that our attack against the PSUCA functionality can be applied to the more complex ideal functionality of a protocol that was proposed by Meta, and I'll introduce that in a bit. We then show 4 more efficient attacks against the same protocol, but we leverage some additional protocol-specific leakage. And finally, we show that our experiments are efficient through an experimental evaluation. In the talk today, I'll focus on the strongest results, which are the leakage-based attacks. A few words on the threat model. This is aligned with the previous works. So we consider a functionality that involves 2 parties, P1 and P2. P2 is assumed to be honest and have a static input, Y, which we call the recovery set. And P1 is allowed to choose its inputs adaptively over multiple protocol invocations. It itself holds a target set T of known information, such as email addresses or phone numbers, and its goal is to infer as much information about Y as possible, given the provided information in T. Now, towards the attack, I'll briefly introduce the protocol functionality and the leakage. So the functionality is called multi-key private matching. Its purpose is to link records across different data sets. And it is a pre-processing step in Apple's private computation solution, Meta's private computation solution, which can be used to measure ad performances. The inputs to these functionality are sets of tuples with some data points, for example, user data. And what the functionality does is match the tuples in the inputs based on shared values within the tuples. The exact matching logic is a little bit convoluted, and it doesn't really matter at this point. But when this matching is done, the functionality assigns labels to these tuples in a way such that two matched tuples are assigned the same label. The parties in the end learn the full set of these labels, as well as a mapping of these labels to their own records. This is what we call the intended functionality of the protocol. It captures Apple's use case, and we propose attacks against this in our work. However, the attacks that I'll talk about in a minute depend much more on the protocol-specific functionality leakage. So yeah, let me briefly introduce that as well. These are again our inputs. And the first thing that happens is that all values in the inputs are hidden by some random hiding function. But crucially, all values in both sets are hidden using the same function. So repeated values are mapped to the same hidden values. And in the second step, these sets are shuffled. This happens independently for each set. This is observed by party P1. So from its perspective, it just sees two sets of tuples with random values. But again, this pattern of repeating values is preserved, even though it is shuffled. Good. This is quite a substantial leakage, and so is our attack goal. And in particular, for these attacks, the adversary manages to recover a partial copy of Y, which contains at least all values that also occur in the target set. And we call this a T reconstruction of Y. I'll briefly outline our approach to achieve such a reconstruction. Assume for now that the adversary runs the protocol with its target set as an input and then observes the leakage that I just described. And recall that to arrive at this leakage, specifically at the part which is called LT, the tuples within the adversary's input are shuffled. However, the values within the tuples maintain their position. So if the adversary can find a matching between the tuples in its input and the tuples in its part of the leakage, assigning plaintext values to these hidden values in the leakage is easy. And finding a T reconstruction is then just an exercise of substituting values in the LY part of the leakage. As a little teaser, this is trivial if the target set only contains one record, that's clear. But this is, of course, quite limiting. So the rest of our attacks either improve on that or, more importantly, deal with finding this matching between the input and the leakage if the adversary's input contains multiple records. And I'll invite you to the poster for more details on that. It's a bit involved. Okay, great. So our experimental setup is also mostly aligned with previous works. Namely, we fix a size of Y and then generate synthetic data sets for varying sizes of the target set T and varying amounts of shared information between the two sets. We measure the attack runtimes without the computation of the functionality and without any network latencies. With that, we basically measure the attack overhead, and this is in general quite minimal compared to the cost of computing the functionality. Our attacks are quite fast, with runtimes between tens and hundreds of milliseconds. On the left-hand side, you can see that the attack runtimes are largely independent of the amount of shared data between the two sets. And on the right-hand side, you can see that the runtime grows linearly with growing target set sizes. And this matches our theoretical complexity theoretic predictions about the attack. Right, now to conclude, I'll briefly outline our disclosure process. So we contacted the authors of the original paper. They acknowledged the leakage and at the same time stated that the protocol currently is not being used in production at Meta. Now, I have 2 points to close. We intentionally distinguish between intended and leaky functionalities. And this is because leaky functionalities arise from decisions during the protocol design process. So if you find attacks against this, that's mainly a critique on these decisions. And what I would hope is that if you design such a system that has a leakage pattern, and you prove it's secure with respect to that leakage pattern, don't just shrug the leakage pattern off as fine and not too bad, as we've seen too often, but think about what an adversary could infer from this leakage. The second point is that even if you deploy a system which has no leakage at all and only outputs the ideal functionality, think about what the intended output of this ideal functionality reveals about the inputs. Yeah, and of course, attacks against these ideal functionalities are sort of a hint that deploying these functionalities at all in certain contexts may not be appropriate. And with that, I thank you for your attention.